All right, let's dive right in. Welcome to today's explainer, where our goal is simple, but absolutely a game changer, mastering the binary search algorithm. Look, if you write code, or honestly, if you just want to understand how computers manage to parse through millions of pieces of data in the blink of an eye, you are in exactly the right place. Today, we're going to act as your coding mentor, breaking down how this blazingly fast logic works step by step. So let's kick things off with a fundamental problem. How do you find a single piece of data without literally checking everything? Imagine you've got a massive physical dictionary and you need to look up the word algorithm. You wouldn't open it to page 1, read the first word, then the second, and scan every single page until you finally find it, right? That's what we call the linear search, and it is painfully slow. Instead, your human intuition kicks in. You open the book roughly to the middle. If you land on the M section, you know instantly that algorithm comes earlier in the alphabet. In literally 1 second, you've completely eliminated the entire back half of the dictionary. You didn't check those pages, you just knew you could ignore them. That exact intuition is the secret sauce to what we're learning today. Section 1, the binary search concept. Let's take that dictionary analogy and turn it into actual computer science. So here is the formal definition. Binary search is a sorted array search algorithm that finds a target by repeatedly checking the middle and reducing the search space to half. Now, the absolute engine of this entire algorithm is that last phrase, reducing the search space to half. Instead of doing the tedious grunt work of checking element number 1, then number 2, then number 3, binary search takes a literal axe to the problem. It chops your remaining workload exactly in half with every single attempt. But wait, pause right here. You've got to remember this golden rule. It only works on sorted arrays. I honestly cannot stress this rule enough. If your data is just scrambled nonsense, this whole logic completely falls apart. Think back to that dictionary. If the pages were ripped out and just glued back randomly, flipping to the middle tells you absolutely nothing about where the letter A is hiding. The math only works if the computer trusts the sequence. Sort your data first, always. Moving on to section 2, step-by-step core logic. Let's look under the hood at the simple internal mechanics. The heart of this algorithm is really just a beautifully simple 4-step loop. Let's walk through it together. Step 1, you check the exact middle element of your array. If it's your target, boom, you're done. If not, we hit step 2. If your target is smaller than that middle number, you go left. You just ignore the right side entirely. Step 3, if your target is bigger, you go right and ignore the left. And finally, step 4, repeat. You just take whatever side you picked and run the exact same process all over again. Check the middle, compare, slice in half. It is a relentlessly efficient loop. Section 3, a practical coding example. Let's actually visualize this halving process with a live dry run. Okay, so here's our starting array. We've got 7 numbers, and notice, keeping that golden rule in mind, they are perfectly sorted from smallest to largest. 10, 20, 30, 40, 50, 60, and 70. This whole block right here is our starting search space. And here's what we're actually hunting for. Our target number is 50. Let's fire up that 4-step logic we just talked about and see how the algorithm handles it. All right, step 1, check the middle. The exact middle of our 7 numbers is 40. Now we compare. Is our target 50 smaller or bigger than 40? Well, it's bigger. And because it's bigger, the algorithm instantly knows it has to search the right half. Because the array is sorted, the computer is absolutely certain that 50 can't be 40, and it definitely can't be any of those numbers to the left of 40. So in a fraction of a millisecond, it literally throws the entire left half right into the trash. Just look at how much our search space has shrunk. We're no longer looking at 7 numbers, we're down to just 3, 50, 60, and 70. With literally one single comparison, we completely bypassed half the work. Now, the code hits step 4, which is repeat, so we execute that loop again on our new, smaller section. Step 1 again, find the middle of these 3 numbers. That middle element is 60. We compare it to our target, 50. Now this time, 50 is smaller than 60. Because the target is smaller, we go left. We eliminate 60, and we drop everything to its right. We've halved our search space for a second time, and now there's just a single slice left. Only one number remains in the entire search space. We check that one remaining middle element, and what do you know? It equals 50. Target found. We're done. Now, I really want you to stop and think about how few steps that actually took. In an array of 7 items, checking every single number one by one would have taken 5 separate checks just to find 50. Our binary search nailed it in 3. Sure, saving 2 steps might not sound totally earth-shattering right now, but imagine if this wasn't 7 numbers. Imagine if it was 7 billion user accounts. That halving effect, it literally becomes a superpower. Which brings us to section 4, the power of O log n. Let's talk about the mathematical payoff here.
The core principle here is that instead of checking every element, binary search keeps dividing the search space in half. And honestly, it really all comes down to that one word, half. When you divide something in half over and over and over again, it approaches 0 incredibly fast. You're not just chipping away at your workload, you are aggressively collapsing it.
And that aggressive collapsing is exactly what's represented by this definition, O log n. This is what we call the time complexity of the binary search algorithm. In computer science, O log n is pretty much the holy grail for searching. It means the algorithm is blazingly fast, specifically because the search space shrinks exponentially. So even as your dataset gets massive, overwhelmingly huge, the time it takes to actually find your target barely even increases. Let's wrap this up with a truly phenomenal mathematical reality. Because of that O log n efficiency, if your search space completely doubles, like let's say you go from having 1 million items to 2 million items to search through, a binary search only requires 1 extra step to find your target. 1. It is staggering when you really wrap your head around it. So I'll leave you with this question. What could you build with that kind of efficiency? Next time you're writing a program that needs to search through sorted data, skip that slow linear approach. Use binary search and let the algorithm do the heavy lifting for you. Thanks for joining me on this explainer, and I hope this makes your next coding project way, way faster.